understanding how they work at this level gives you a lot of information about how to handle some of the kinds of problems that come up. But I thought we would work for a little while here with floating point numbers. Now, that was before I came into the class, but I assume you did talk about the floating point format a little bit?
Yeah, I think it was mentioned.
I think it was mentioned, but we don't.
Okay, well, we're going to learn something about it. The leftmost bit is the sign bit. It's one bit. We have an exponent here, and the remaining 23 bits is something that goes by various names. It used to always be called the mantissa. Sometimes it's called the significand. Various other things that happen in there. Let's put a number in floating point format and see how it works out. For this example, I'm going to work with an integer. Okay, we'll take x to be, we'll take a pretty good sized number, just for the fun of it. If we want to represent that as a floating point number, first thing we have to do, of course, is convert that into binary. Now, once again, in light of other things, going directly to binary is a waste of your effort and time. Go to either octal or hexadecimal first, because from there to binary is just a write down. So we'll go to hex. 37, 1. And then 16 into 14873. 9 is 144. 2. And 929. And 16 into 57 is, so this is 3919D in hexadecimal. Now I can write that in binary then, just by converting each individual hexadecimal digit. So I get 3, 9, 1, 9, D in binary. Now,
Really quick,
yeah,
I just did it on a calculator, and it's 3A19B.
3A.
Yeah.
can't see,
We're just learning how to do it.
let's see here. The number is 237981. Yeah, it is 3A. Oh, yes. That should be an 8. 6 times 8 is, okay. 8, and so this is a 10, which we would write as an A. And so we have 1010. So there we go. Watch my arithmetic. No guarantees on anything there. Okay, now, to get this thing into proper form, we just write it with a decimal point there, binary point if you wish. Decimal refers to base 10. Now, we normalize the thing, that is, we get that point over here, so it's 1.1101, 0.000011001101 times 2 to some power. What power? Well, in base 10, multiplying or dividing by 10 moves that point one place. Same thing is true in binary. Multiply by 2, it just moves it one place. Multiply by 2 moves it to the right. Divide by 2 moves it to the left. How far do I need to move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. Each one of those powers of 2 would move that point one place to the right. So that's the number I'm going to store. The exponent that I actually store, however, is not 17. They've chosen another interesting way of doing it. We store this exponent in what's called excess 127 format. That is, what we actually store is this exponent here plus 127. Okay, so if we look at 127 plus 17, well, 144 in hexadecimal is 90. So what I'm going to store here is 90. And I started with a positive number, so I'll put a 0 there. Now the thing is stored down here in these 23 bits. This part here is not stored.
The 1 decimal? Or
Right.
1 decimal.
Just the 1 and the decimal. The leading 1 is not stored. It saves you one place of storage. And of course, there is no bit that represents the point. The point is just understood to be there. So we store 1101, 4 zeros, 1100, 11101. And that's what? That's 17 digits, so I need 1, 2, 3, 4, 5, 6 more zeros. Okay. That's the way we store the numbers. Okay, any questions about that? Now, we're gonna mess things up here a bit. I'm gonna show you the easiest way to store and to determine this mantissa for a fractional value. As I go through the book, the only ones he does in there are the easy ones. We'll do one that's not so easy.
So the mantissa is what comes after the decimal?
Yeah, basically, it's everything after this, filled out to 23 bits.
From left to right.
Let's see. Well, let's get something that doesn't come out really even. Yeah, that's probably enough. Let's not go beyond that. Pi. See how we would represent pi in this system. Well, the integer part of it is easy. It's 3. 1, 1. Now, you can start looking at that fractional part. And you know, in decimal, in base 10, why this is 1/10. For hundredths, for over 10 squared. 1/1000th, 1/10 to the third, so on. They're just increasing negative powers of the base. Well, we do the same thing in binary, except the base is 2. So the first digit after the point would be either 0 or 1 over 2. And then 0 or 1 over 2 squared, 2 to the third, 2 to the fourth, so on. So as you look at the way things are kind of done in the book, we can 1, 5, 9, 2, 6, 5. 1/2 is 0.5. It's not as big as 0.5, so my first digit out here is going to be 0. Come down 1/4, 0.25, still not that big, so the next digit's a 0. 1/8 is 0.125. That's less than this one. So I'll put in a 1 here and I'll subtract 125. Okay, that's how much I have left to put in there. Well, let's see, 1/16 is 0.0625. Well, that's bigger than this, so I won't have a 1/16. Now I can go to 1/32, 0.3125. That's still too big, so I put in another 0. 1/64, 15625. That
Isn't
one
it
works, so I would
6125?
have a 1.
Or 6.
Did I do that right? sheet and check with the arithmetic here. 64th. 015625. Yeah, that's right. Okay. Minus 2 is 6. Now, okay, everybody convinced that's a long and tedious and messed up way to do it?
I guess we don't have to know it.
You what?
We don't have to know it.
No, this isn't the best way to do it.
Okay.
Let me show you how to do it. We'll take our 3, instead of going directly to binary, I'm going to go to hex. So I have 1415925. I'm going to multiply that by 16. Why 16? Because that's the base I'm going to. 59265. I get 2.265482. I will take that 2 and put it here. I will take the 2.65482 down here and multiply that by 16. Okay, I take the whole number part over here, take the fractional part, multiply that by 16. Take the 3, 963,494. And I get 15.415910. Take the 15, which is an F in hex. 415910. How long do I have to keep going? It may never come out even. Try it with 1/10. It never does. Never does come out to a pure integer. Notice I've got to come up with 23 bits. Each hex digit gives me 4 binary digits. So I need no more than 6 hexadecimal digits. Well, maybe a little bit more, because this one may not actually occupy the full 4 bits. So typically, if you go until you have 7 hexadecimal digits, you've got all you need. 1, 2, 3, 4, 5, 6. I need one more. So I have 6, 5, 4, 5, 6, 6. All I want is the 10A in hexadecimal. Okay, it's a nice scheme, and it allows you to make the transition pretty quickly. Again, then going from that hex to binary, isn't particularly difficult. The 3, 2, 4, 3, F, 6, A. Now, just out of interest, notice here that this started 001, 001, 001, 001. I was all right to that point. But boy, that's really slow. And you see what I ended up with here now, after getting to this 1, is really small, so it's going to take a few more digits, well, quite a few, before I get another 1. So it seems to agree. Okay, so we normalize this thing, and we get 1.1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 0, 1, 0, 1, 0. I only moved it one place, so it's times 2 to the first. Okay, so what does my number look like? Well,
A headache.
it's 0, it begins with 0 because it's a positive number. The actual exponent that I store I know what the problem is. There are a couple of different ways that you can look at the way these things come together. Floating point data type, there we go. One of them depends on where you assume this point is. If you have it over, if you assume it's over 1 beyond that, then your exponent comes out a little bit different. My exponent that I store, the stored exponent is 127 plus this.
So if you had a number that was less than 1, so it was a fraction basically, would your
Exponent be negative, yeah.
yeah, and so you would take 127 minus your exponent, or it would be like
Well, it'd be 127 plus a negative number.
right.
Yeah. Yeah, we'll do one of those here, I hope. Okay, 128 is 70 in hex. So I have 70. There's my exponent. Now I store the mantissa part, so I just begin here and just count bits as I put them in until I get to 23 bits. Now let's see, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Notice that this got lost. Because there's a limit. That's the thing that actually limits, when you're working with floating point numbers on the computer, it limits the number of significant figures you can actually work with. You get typically, on a float, about 7 significant figures. And it's because of this limited size. So if you're gonna go to a double that gives you more precision, what are you gonna do? Somehow or other, you gotta store more than 23 bits. Well, there are a number of different non-standard implementations on that, but typically you take another 32-bit word, and in some cases, the exponent remains the same, and the other 32 bits all just go into the mantissa, and so you have to go a lot farther than this to fill out another 32 bits. Some of them will actually increase the size of the exponent when you go to a double. We'll see how this limits the size of a number that you can work with in here. Okay, if we look at how this might be represented, if you got a hexadecimal printout of a memory location containing pi, this is what it would look like. It's just a bit pattern. Okay. Now, yeah,
Does the LC3 work with floating point, because we only have 16.
not as a native data type, no. It does not.
We only have 16.
In fact, it was a long time in the business before they got any hardware floating point systems. Most of them up until early to mid-70s, all the floating point stuff was done in software. It was much later than that in the PCs. The PCs were initially integer processors. Let's see.
Is exponent just the 8 digits?
Yes.
So it's like the main part of the number? I'm just trying to distinguish it between what
Define what you mean by main part.
Well, I don't know that I know. My idea of exponent is, x squared. The 2 is the exponent.
That's correct. The exponent that you're working with here is the exponent on 2, which tells you where to position this thing to get the number that you're looking for.
So the exponent tells you where to put the decimal.
Yeah, in essence, because you can't store that point. There's no symbol for it.
Just like scientific notation.
Yeah, this is just a scientific notation. That's all it is. It's just a base 2 scientific notation instead of base 10, but it's the same scheme, same idea. Let's see. Oh, we still have that number up here. Did somebody write down what this number was that I figured it was 200 and something thousand?
237,981.
Okay. That's what it looks like. suppose we want to take that number and add pi to it. Okay, with no hardware support. Think that, no, well, it was the first advanced assembly language course that I taught. That was their final assignment, was to write code that would add those things together. Here's what you have to do if you're going to add those together. We want to add 237986.
1.
91.
Yeah, 981.
981 plus here's what we have to do. Let's see. I'm not going to have enough room. We're probably not going to get through the actual computation of doing this thing in any event. Well, the first thing we have to do is split these things up, get the exponent extracted. I'm going to write it in hex. Got a 90, and on this one we have a 70. And then we have the mantissa. And as we do this, I'm going to put that hidden 1 back into it. Remember, this 1 here ahead of the decimal point we don't store. So the actual mantissa for this thing, I'm going to write it as 1 point, and then we'll write this in hex. Recognizing that that last one there is only 3 bits. So we've got 1101, which is a D 0C E80. And now for this one, again, it's 1 point.
Those last two are lost.
Oh, yeah, the last 2 are, right. Okay, so we've got 9, 2, 1F. B. And to make this thing come out consistently, why instead of a 1, I would put a 0 there, so I've got a 4. Recognizing that that's 1 bit farther than I really am. Now, in order to add these things together, just like if you're adding things in scientific notation, if you have 2.34 times 10 squared plus 3.91 times 10 to the third, you have to somehow or other line up these things. can make these things the same, then you can just go ahead and add these things together. Well, what we do, times 10 squared, I would have 39.1 times 10 squared. Or I could do this as 0.234 times 10 to the third. In either case, the number is 234, see? If I move it 2 places to the right, gives me that. Here, if I move 3 places to the right, I've still got it. And then 3.91 times 10 to the third. Now I can add them. Okay, we have to do the same thing here to add these things in the floating point format. It is exactly the same idea as the scientific notation. Now, what we usually do, and it gets a little hard to track down, we do it this way. We take the smaller exponent, shift those numbers to the right, and increase the exponent by 1 until they line up. Okay, so what I will do here let's see. That's what I had, and my exponent is 70. If I shift everything to the right 1 place, that's just going to disappear now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23. Well, now I have an exponent there of 7.1. Shift it again. I would have an exponent of 7.2. How far do I need to go? A long ways.
Can't we just use a calculator?
Well, another thing to look at there, if you shift 4 bits at once, that's just shifting your hex digits over. So you see, if I go in hex, 0.1, 921 FB4. That would give me an exponent of 7.4, because I just moved it 4 places. 01921 FB4 78 0019 FB4 I've got an exponent of 8 zeros. Four. 8. 8C. 92FB490. Aha. Now let's see. What did I have here? On the other one, I've got 1.BOCE80. And so now I'm going to add to that 1, 2, 3, 4, 5, 6, 7. But I can't store anything beyond that. Something isn't quite right here, to be honest with you, because pi should not have disappeared completely. But the point is, in floating point numbers, if you add a very small number to a very large number, the small number gets lost. It just doesn't show up, period. In fact, you can even get to the point, and I'll show you this point on Monday, where you can take an integer, a whole number in there, represented not as an integer, but as a floating point number, add one onto it, and it won't change. In other words, there are consecutive integers that cannot be represented as floating point numbers. That is a source of some of the most common errors and problems working in a high-level language. I had some students one time that wanted to find pi, by those of you that have had calculus, by integrating the portion of the unit circle in the first quadrant. And they did 10 intervals and got a fair answer. Did 100 intervals. Yeah, it's getting better. Got 1,000 intervals. Cool. Can we do 1,000,000? Well, the administration won't let you take the computer for that long, but I'll see if you can come in on Saturday and do it. Okay, they did. Came in on Saturday, and in 1,000,000 intervals, the answer just went all to pot. Absolutely no accuracy in that at all. Why? Because after a certain point, they were just adding very small numbers to very large numbers, and they just disappeared. Just disappeared. And this is why. The way you add those two floating point numbers together is you shift around until the exponents line up, and as you shift one of those numbers, some things are going to get shifted out the right end of that 23 bits. You've only got that much to work with.